So next up is Stephen Green. He's going to tell us about reconstruction techniques in particle physics.
Thanks. Hi, so good afternoon, everyone. My name's Steve Green, and I work in the High Energy Physics Department of the Cavendish. And today, I'll be giving a talk on the Pandora multi-algorithm approach to pattern recognition in high energy physics. Now, high energy physics is the study of the building blocks that the universe is made of, and the job of a particle physicist is to find out how these building blocks go together. Studying the properties of what our universe is made of will help us to answer such interesting questions as why is the universe made of matter, how are the fundamental forces related to each other, and what exactly are dark matter and dark energy. Now, there are two types of particle experiments that particle physicists often perform in an attempt to answer these questions. And they are collider experiments and neutrino experiments. This is not an exhaustive list, by the way. There are others, but these are some major ones that Cambridge is involved with. Now, collider experiments, such as the Large Hadron Collider, aim to smash particles together in an attempt to break them apart or make new ones. On the other hand, neutrino experiments examine the interactions of neutrinos with a large volume of material, a large volume of sensitive material, such as liquid argon. And the study of neutrinos requires this whole new category of experiment because neutrinos don't interact very strongly with anything, and so trying to collide them together simply wouldn't work. Now, over the years, a common trend in detector technologies used at both collider and neutrino experiments has emerged. The granularity of the detectors being used is getting finer and finer. This means that we are getting better and better images of the particles that we're interested in looking at. On the top of this slide, we've got examples from the of collider experiments. On the left here, we've got the Opal experiment, which was about 30 years old. And on the right, we've got the linear collider experiment, which is a next-generation particle collider. And below that, we've got a similar comparison for neutrino experiments. On the left here, we have MINOS, which is about 13 years old, or began taking data 13 years ago. And on the right, we have Microboon, which began taking data 3 years ago. Now, if we just contrast the images on the left and on the right, you can actually see that there is a huge difference and that the resolution of the things that we're looking at really has vastly improved over time. Now, this additional information is extremely useful for studying particle physics. In previous generations of experiments, a lot of information was lost because the granularities of the detectors being used was simply too coarse. The particles being measured were simply too close together for the detector to be able to distinguish them. With modern-day particle colliders, we can now really track the flow of individual particles in these experiments. And these details help particle physicists to fully understand what is going on when particles interact, and that is invaluable in our search for new physics. This advancement does present a new challenge. The more information we get in these images, the harder it becomes to figure out exactly what's going on in all the detail. The Cambridge High Energy Physics Group is tackling this challenge for both collider and neutrino experiments. So firstly, let's consider collider experiments, and in particular, the linear collider experiment. The linear collider is a proposal for the next generation particle collider for after the Large Hadron Collider has finished taking data. The main goals of the linear collider are to study the Higgs boson and the top quark, as well as to search for new particles such as supersymmetric particles. And the linear collider will achieve these goals by providing precision measurements of the interactions between electrons and their antiparticle positrons. Now, broadly speaking, the layout of all particle collider detectors, and the linear collider is no exception to this, consists of two types of components, trackers and calorimeters. Trackers record the paths of charged particles passing through them by measuring ionization currents, while calorimeters measure the energy of both charged and neutral particles. The detailed images, such as this one here, of the linear collider, detailed images produced by the linear collider detector allow us to track particles made at the collision point, so that would be right at the center of this cross-section, throughout the entire detector. And this will allow us to fully understand what was produced at that collision point. And so it will really aid our search for new physics. Now, charged particles at the linear collider detector produce both tracks and calorimetric energy deposits. And in order to get a full picture of what happened at the interaction, we need to associate these two measurements together. Now, the human brain is extremely good at doing this, extremely good at image reconstruction and making these associations. For example, I'm sure I didn't need to tell most of you that this track here being measured in a tracker is actually associated to, is produced by the same particle that made all of these calorimeter hits. You probably just did that automatically without even thinking it. Now, that's great, but the problem particle physicists face is that we want to look at loads of these interactions and loads of these events. So it's unfeasible to do this all by eye. And so instead, we need software to make these associations and do the image reconstruction that all of your brains will have just done automatically. The Cambridge High Energy Physics Group has developed the Pandora software package for this very task. Now, from this example, the problem may look quite trivial. You're thinking, it's not that complicated. I imagine I could probably do something like that. However, if we take a quick look at a high-energy interaction, you can see the problem is much nastier than that little trivial example just showed. However, the Pandora package has solved this pattern recognition problem and is now the cornerstone on which the linear collider reconstruction is built. The physics case for advocating the construction of the linear collider could only be made thanks to the work done here in Cambridge. Now, another challenging pattern recognition problem that the Cambridge HEP group is tackling is reconstruction at the Deep Underground Neutrino experiment, DUNE. And as the name suggests, DUNE is a neutrino experiment. DUNE is the next large-scale global project in particle physics. And it has the potential to make groundbreaking discoveries in the area of neutrino physics and astroparticle physics. Here's a short video giving you an idea of the scale of DUNE, and hopefully it will work. Awesome. The first step in the DUNE experiment consists of the production of a beam of neutrinos in the Long Baseline Neutrino Facility in Fermilab in Illinois. This beam is then fired over 2,100 kilometers to the Sanford Underground Research Facility in South Dakota. And there we go, you can see it being fired. Once there, some of the neutrinos in that beam will interact in the DUNE detector, allowing us to measure them. The interactions are measured using highly sensitive liquid argon time projection chamber detectors, or LAR-TPCs. This detector contains approximately 70,000 tons of liquid argon, and it will be located approximately 1.5 kilometers underground to help reduce background from cosmic ray particles. Now, pattern recognition is an essential aspect of DUNE because of how LAR-TPC detectors work. LAR-TPCs measure ionization currents produced from charged particles as they pass through the detector. In this sense, they are like the trackers used at the linear collider experiments. However, they typically have much finer granularity and so produce much more detailed images of the interactions taking place. And here's another short clip explaining how LAR-TPCs produce their measurements. So as neutrinos enter LAR-TPCs, some of them interact and produce other particles. And if these particles are charged, ionization electrons from those particles will drift to one side of will be produced and will then drift to one side of the detector because of the presence of an electric field. These electrons are then collected and measured, and they give you an image of the interaction that took place. Now, pattern recognition is needed at LAR-TPC experiments because of the images created from a LAR-TPC is a 2D image. And to study the interaction in full detail, we want a full 3D reconstruction. And more than that, we want to actually make this 3D image in any part of this 70,000-ton detector. And this is quite a challenge. Unlike in the animation, LAR-TPCs actually produce 3 sets of 2D images. The principle is identical in the way in which they are made. And so to actually, by producing these 3 lots of 2D images, LAR-TPCs give you enough information to actually record the 3D event. And however, the job of reconciling all these 3 different views to create a consistent 3D event is highly non-trivial. The Cambridge HEP group has been adapting Pandora to tackle this challenge, and now Pandora contains over 130 algorithms and tools aimed at reconstructing neutrino interactions. In both the linear collider experiment and at Dune, the pattern recognition problem is too difficult for a single clustering algorithm to solve. Therefore, Pandora adopts a multi-algorithm approach, where each algorithm that's used is relatively simple to avoid making mistakes, and is designed to gradually build up the event. As the picture of the event deepens, more sophisticated algorithms can be applied that incorporate physics and detector knowledge. And the Cambridge HEP group is working to extend this remit to its approach and to include new computational developments such as machine learning. Now, at this point in time, the LAR-TPC reconstruction project is far from finished. Here in Cambridge, we are continuing to develop Pandora for LAR-TPC experiments to make it better and better. In the short term, a large part of this work involves optimizing Pandora to work with a prototype of the Dune detector that's being constructed and tested at CERN later this year. And alongside this, we're continuing to support and develop Pandora for ongoing neutrino experiments such as microboon. Now, the development of finer granularity particle detectors is significantly helping to advance our knowledge of particle physics. The work going on here in Cambridge is making major strides towards solving these pattern recognition challenges that are presented by these finer granularity detectors. And this is truly essential for full exploitation of the experiments particle physicists are performing. Thank you for your attention.
Thanks, Steve, and perfect timing.
Thank you.
Are there any questions? Careful with catching.
Just the way, are these neutrino experiments easier in that there's not so many events per second? I mean, in some of the experiments I gather, the Large Hadron Collider, there's astronomical numbers of data coming in every second.
I believe that there is still quite an issue with the Dune detector, as I think the rate is still quite high, so you are getting numbers, a sizable number of particle interactions per second. So yeah, it is still a challenge. It is less than at the LHC, but.
There's one question right at the back there. Henning can catch very well. No, he can't.
It was bound to happen.
Not that one. No. Why is it necessary in this Dune experiment to send the neutrinos over 1,000 kilometers before detecting them?
That's because neutrinos oscillate in flavor, so quite unusually, they may begin in one flavor, say an electron neutrino, and then after walking a certain distance, they may oscillate into one of 2 other different types of neutrino. So what we're interested in measuring actually is how the rate of neutrinos changes into the other different flavors of neutrino. And to do that, you need to travel a sizable distance because of relativistic effects. And so that's why you have to fire at a very long distance. And we're also interested in doing the same for antineutrinos and comparing the 2.
Okay, I see no other hands up, so let's thank Steve again.
Thank you.